suppose R is a relation from A to B, and S and T are both relations from B to C. And we're supposed to prove that S composed with R minus T composed with R is a subset of S minus T composed with R. Okay, let's try and figure out what this is talking about. So we have three sets, A, B, it's not very good, B and C. And we have relation R from A to B, and a couple relations S and T from B to C. And we're supposed to show that basically if we have an element that's in S composed with R but not in T composed with R, okay, so it's in this relation from A to C, S composed with R, but it's not in this relation from A to C, T composed with R, then that means that it's in, well, it's in the composition of S minus T, and then that relation composed with R. Okay, so this seems sort of at least mildly plausible, but it's a little bit hard to be fully convinced just by this picture, because you have to really think about which elements are in the various relations. Okay. So this is one where it's really going to help us to make our table of givens and goals. There's kind of a lot to keep track of, so this will help us stay organized. So we have three relations, R, S, and T, in the appropriate places. We have our subset statement to prove, and we take the definition of that. And yeah, we do have for all a C out front, which I'm sort of ignoring here. So we're going to let A and C be arbitrary and prove that if AC is on the left side, then AC is on the right side. And I'm choosing AC because these are both relations from A to C. All right, we'll do direct proof to get that conditional. And then to prove that AC is in this difference of sets, we want to show that it's in the first set, S composed with R, and it's not in the second set, T composed with R. Excuse me, we're not showing, we're assuming that. And then we're proving that AC is in this composition, and that means there exists some B kind of in between in the set B, I guess, such that AB is in R and BC is in S minus T. Okay, I don't have to say that little b is in the set capital B here, because that's just implied by what's in here, right? If AB is in the relation R, then the second coordinate certainly has to be in the set B. Okay. All right, and then we have these element of a composition statements, and if we break them up on separate lines, then the first one gives us something quite similar to what we had over here. There exists a B such that AB is in R and BC is in S. And the second one, well, something similar again, but I'm going to use a different bound variable B prime, and this is not contained in the composition, so I'll put a negation symbol out front. Okay, what are we going to do with all that? Well, we can certainly do existential instantiation on that one to get a B naught, and then we can move the negation symbol past the existential quantifier to make it a universal quantifier for all B prime, and then we have to negate what's inside, and for that we can use De Morgan's law to change the and into an or, and so we just take the negation of each of the individual statements inside. And over here we we can decide for which B value are we going to prove this, right? And it looks like B naught is the free variable we have sitting over on our given side, so probably we're going to prove this for B naught. Okay, well, let's just break that up on separate lines, and then let's think about which value of B prime we want this for. It's probably B naught, right? That's the that looks like the thing that's involved here. So we'll do universal instantiation where B prime is B naught. And then just break that up on a couple lines so we have those two goals. And we're pretty close because we know that AB naught is in R, and we also know that either it's not in R or BC naught is not in T. And so using, remember what that's called? There's a disjunction, so this is disjunctive syllogism. We know that this first option's not the case, therefore the second one must be. Okay, so we can conclude that B naught C is not in T. And that's everything we need. We have our first goal right there. And then these two statements together give us that B naught C is in S minus T. Okay, let's type up a proof. Already saying here that, well, I'm not even bothering to say let AC be arbitrary, and I'm just going ahead and doing direct proof. So suppose AC is in that set difference, and we're going to prove this. And from there, the next thing was we had to write out kind of what being in that set difference means. And let's write that first. It's a good start. So I just say we know that, based on what we're supposing up here, AC is in S composed with R, and AC is not in T composed with R. All right. And then from the first half of that, which showed up in the first line here, via an existential instantiation, we get that we have this B naught such that those two statements are true. So therefore, based on the first thing we just wrote in the previous line, there exists some B naught such that A B naught is in R and B naught C is in S. Okay, and then from the second half up here we got down to this statement, and that, when we dealt with our negation, turned into this, right? So let's go ahead and mention where we got to there. So from this first statement got me to this therefore, and then this one I'm talking about next. So I'll say moreover, for all B in B. Okay. I have B prime there. Maybe I should stick to that so we don't get confused. So for all B prime in B, either A B prime is in R, is not in R, right? Not in R, or B prime C not in T. All right, and then we know which one we are in this case, because if we apply that to B naught, we get here, and we knew that A B naught was in R, and so that cancels out that possibility, and disjunctive syllogism gives us that one must be the case. Okay, so we'll say therefore, because A B naught is in R, and because of what I just mentioned in the previous line, it follows that B naught C is not in T. And now we just have to combine things. So because let's see, what do I want to say? I'll mention that these two get us to B naught C being here, right? So because B naught C is in S, and we have that up here, and it's not in T, we just proved. We have that B naught C is in S minus T. And what was our goal up here? It was that AC is in this composition. Okay, so we should say how we're going to get from this, and then this goal, which we already mentioned in our proof. Don't have to say that again. We should just mention that this does get us up to our goal. Okay, in case our reader doesn't notice that yet. So say because A B naught is in R and B naught C is in S minus T from the previous line, it follows that A C is indeed in S minus T composed with R. Okay. And that finishes the proof.